Welcome back. In this video, I will go over the theory and experimental setup for determining zeta potential by microelectrophoresis. When we have a surface, it is usually charged, and in this case, we depict a charged surface with a positive charge. And because of that charge, it will attract negative ions to absorb onto the surface to balance the charge. To understand the electropotential difference, we can define the variable psi as the electropotential difference between the dispersing medium and some particular location x. And the dispersing medium's potential is defined as the reference potential 0. So at the inside of the dispersing medium, has psi infinity 0. Helmholtz model is the simplest model to describe the electrical double layer. It assumes that when we have a charged surface, then the counter ion will absorb to the surface and form an electrical double layer that has a distance of delta apart. So we have a true surface potential of psi of 0, and at the absorbed layer we have psi of delta. And then beyond that, we will go to psi infinity, the reference charge at the dispersing medium. The Helmholtz model is a naive one because it did not account the counter ions that is diffusing within the dispersing medium. The Gooey-Chapman model models the electrical double layer as a diffused counter ion at the dispersing medium, so there is no specific absorption onto the surface, but the counter ion is diffused throughout the dispersing medium. And the electrical potential can be modeled by exponential decay that decays to the dispersing medium's potential that we set as reference 0. However, Gooey-Chapman's model does not take into account of the specific absorption of counter ions onto the surface, which usually occurs. Therefore, Stern proposed a model where at the charged surface, there is a specific absorption of the counter ion onto the surface according to Langmuir absorption. This layer of counter ions that absorb onto the surface is called the Stern layer. And the Stern layer's counter ion does not neutralize the surface exactly, so there will be a diffusing layer of counter ions at the outside of the dispersing medium to neutralize the charge on the surface. So the electrical potential at the surface is psi 0, and it drops to psi of delta at the Stern layer, and it decays exponentially to the dispersing medium's potential, which we set as 0. We will be using the Stern model because it provides a more accurate description of the electrical double layer. Now we can define the zeta potential. Zeta potential is the potential difference between the dispersing medium and the slip plane, and the slip plane is where the medium's or the liquid's velocity equals to 0. The slip plane is usually slightly further out into the solution compared to the Stern layer. So for example, Stern layer and the Stern model is around here, then the zeta potential, the slip plane, is maybe right around here. This is the slip plane. The zeta potential is the potential at the slip plane. And because usually the slip plane and the Stern layer is so close to each other, you can usually approximate them so that the potential at the Stern layer is approximately equal to the zeta potential. Consider a charged immobile surface. Here it's a negative charged surface such as glass. Its counter ion, the positive ions, will have a Langmuir absorption onto the surface and a diffuse layer. The diffuse layer of ions, if subjected to an electrical field, if we put a cathode and an anode here, then the ions would migrate toward the negative electrode or the anode. And the migration will set the liquid into motion by the action of viscosity. And this phenomenon is called electroosmosis, where the liquid moves and the solid is at rest. And the driving force of the liquid moving is the ions moving due to the electrical field. Now consider a charged solid particle. In this case, the charged particle is negative. So under electrical field, it will migrate to the positive charged cathode, and that will set the particle into motion. And this phenomenon is called electrophoresis, where the solid particle moves whereas the liquid is at rest. Electroosmosis and electrophoresis is phenomenologically the same thing, whereas one is liquid moves and solid is at rest, whereas the other is the solid moves and liquid is at rest. Because motion is relative, they should give similar results, and they indeed give the same zeta potential during the slip plane. To determine the zeta potential from electrophoresis, we can first define the electrophoretic mobility, U of E, that is equal to the particle velocity divided by the electrical field strength. And the particle velocity is something that we want to measure, whereas the electrical field strength is something that we already know. After some analysis, we can arrive at two limits. One limit is the Helmholtz-Smoluchowski limit. Where it has kappa A greater than 200, where kappa is the bit length and A is the particle radius. And the electrophoretic mobility in that case is the dielectric constant of the medium multiplied by the permittivity of free space and multiplied by the zeta potential divided by the viscosity of the medium. So the dielectrical constant is the medium, which should be known because it's usually water. And the permittivity of free space is also known. This is a universal constant. The potential is something we want to know. And viscosity of the medium is also known. For example, if we have water. And the other limit is the Huckel's limit. When kappa A is smaller than 0.1, then it will be the term multiplied by 2/3. Using this equation, we can solve for zeta. For example, if we are at the Helmholtz-Smoluchowski limit, then we can solve for zeta, where we have zeta equals to moving velocity at the top, then electrical field at the bottom, and epsilon, epsilon naught bottom, and mu at the top. So we can solve for the zeta potential. Since the viscosity is known, electrical field is known, dielectric constant is known, the permittivity of free space is constant, also known. We just need to measure the particle velocity to get the zeta potential. When finding the potential, some ions have concentrations that will determine the surface potential of surfaces. So those ions are called potential determining ions. For crystal and solid, the potential determining ions are the lattice ions, whereas for oxides, the potential determining ions are the hydroxide ions and hydronium ions, which can be indicated by the pH. Now let's consider oxide because its pH determines the surface potential of oxides. We can define a term called the point of zero charge, or PZC, as the pH at which the surface potential psi of 0 is equal to 0. So when the pH is smaller than the PZC, the surface potential is greater than 0, and the surface charge is positive. If the pH is greater than the PZC, then the surface potential will be negative and be smaller than. We can also define the isoelectric point, or the IEP, or sometimes called the PI, as the pH at which the zeta potential is equal to 0. And because zeta potential can be approximated by the potential at the Stern layer, we can also state it's the pH at which the Stern layer's potential is 0. And recall that when zeta potential is 0, the electrophoretic mobility is also 0. Then the particle's velocity will also be 0. These are equivalent descriptions of the isoelectric point. To determine the zeta potential, we can use the electrophoretic mobility at the Helmholtz-Smoluchowski limit, and then we can derive the zeta potential in terms of constants of viscosity, the dielectric constant, the permittivity of free space, and electric field that we have known. And the one thing that we left to measure is the particle velocity. We can measure the particle velocity using a dark field illumination microscopy shown here. We can use the eyepiece to see how the particles move within an electric field. For example, in here we have colloidal particles, and we have an electrical field that has a positive cathode and a negative anode, and the particles will move in the electric field. However, we need to be specific about which plane we're observing the particles in, because electrophoresis have solid particles moving only when the liquid is at rest. So the velocity of liquid v of x is 0. However, the driving force is not only the electrophoretic process, where we have the primary driving force of electric field onto the left, but there's also a driving force to the right, where because all the masses should be conserved at steady state, and the liquid won't just move to the left forever, so a back pressure will be building up to the right. So the velocity profile of the liquid v of x is shown here, where we have at the edges there is a back pressure where the velocity is going backwards, where in the middle there is mainly driven by the electrophoretic process. And at the intersection of them, we have stationary planes where the velocity v of x is equal to 0. And when we solve, after analysis and solving for it, we can find the location that it is located at. And we want to determine those locations and observe the particles at those locations where the liquid is at rest, so we can be sure that the particle's velocity is its true velocity without any edge effects. To determine the particle velocity, the eyepieces on the microscope will have grids, for example, like this. And you'll see light points of colloidal particles. So when you don't have any electric field, when the electric field is 0, then it will be doing some Brownian motion on there. And then you will select a particle before it starts moving, and then turn on the electric field, say, let's say 5 microvolts, and then it will start moving. And you will count how many cells it has passed for a given interval of time. For example, if I have a particle starting here, maybe I want to count till here, so that I'm sure that it has passed 2 grids. And then you want to record down the time that it goes in those 2 grids. We can also use laser Doppler electrophoresis to determine zeta potential with more sensitivity. Essentially, it shines a laser through the device and then goes to the Bragg cell and the mixed-fixed mirror and shines onto the cell that contains a series of refraction fringes. And at the refraction fringes, if the particle moves, it can be detected by the light, so it can calculate the zeta potential more sensitively. And the common instrument for using laser Doppler electrophoresis is called the Zetasizer, shown here. Because the measurement by the Zetasizer is far faster, we can determine the zeta potential of many samples relatively quickly. So in this case, we can determine the isoelectric point using the Zetasizer. So we've plotted zeta on the y-axis, or the electrostatic mobility on the y-axis, and on the x-axis pH. Then for different electrolyte concentrations, we can determine the isoelectric point. For example, if we have this, since the isoelectric point is defined as the pH at which the zeta potential is 0, then this is called the IPE, or PI is the isoelectric point. For example, this might have a concentration of 10 to the negative 1 molars, and you might also want to do another one, solution with 10 to the negative 2 molars, and so on, so you can determine the isoelectric point. In this video, I went over the theory of determining zeta potential and the experimental setup for finding zeta potential by measuring this particle's velocity. I also introduced the concept of an isoelectric point and the point of zero charge, where it sets different potentials to 0.